In this video, we're going to go over the basics of linear regression, including how to conduct linear regression using Excel. The goals of this video are to first introduce regression terminology, second, to understand how to interpret regression results, third, how to infer if regression results are different from chance, fourth, how to use regression results to make predictions. We will not be generating regression results in this video. I will post a separate video on how to do that using Excel. I will begin by addressing the question, what is linear regression? Linear regression relates changes in a dependent variable, often labeled y, to changes in one or more independent variables, typically labeled as x. Simple linear regression has only one independent variable. Multiple linear regression has more than one independent variable. In the simplest model, we're trying to relate the expected value of the dependent variable to the values of the independent variables. So to give you a sense of what's going on, let's think about some data. Here I created some fake data where I drew the x value uniformly distributed between 0 and 1. I constructed a standard normal error term, and I added them together. And the object of the exercise now is to figure out how exactly did I do that? What is the slope of the relationship between x and y? You can think of linear regression as trying to draw a line, and we want to find a line that we call the best fitting line that connects the x values of our data to the y values. And what we're going to do is we're going to find a line that minimizes the square difference between our data, the dots, and our prediction, the blue line. So we end up with a regression line that illustrates our relationship between x and y, and we will see in a few minutes how to interpret the slope and the intercept of that line. What I'm actually doing, well, here you can see how I've taken 2 points in red, and I've drawn an arrow connecting them. This arrow links an actual data point to its predicted value on the regression line. And for every dot on this figure, there's an arrow just like it. And what we're trying to do is we're trying to find a way to minimize how long all those arrows are in total. And we're going to add them up, and we're going to add up the squares of them because that ends up working out nicely mathematically. Other forms of regression will use different ways to combine these errors, the differences between the actual and the predicted point, in order to infer or estimate the coefficients. Now let's turn to interpreting regression results. Regression results are typically presented in a tabular form, like what you see here. And you want to look for the coefficient or the point estimate. And that is what we call the slope of the regression line. So here you see that the estimate on x is 0.972. And what that means is that for every 1 unit increase in x, our predicted value of y will go up by 0.972 units. The intercept is going to be the expected value when x is 0. So our intercept here is 0.005. Now when I created the data, I used an intercept of 0 and a coefficient of x of 1. So this is very reassuring. This is very close to what we would expect to see. And then we have the columns standard error, t-value, and probability greater than the absolute value of t, which measure how certain we are about the estimates. And you'll see these values referred to in different ways. Sometimes standard error is presented in parentheses after the estimate. Sometimes you don't get a t-value. You might get what we call a z-value instead, which is the same concept, just drawn from a different distribution. And sometimes we'll call the probability greater than the absolute value of t, that final column, we might call it the p-value. In all cases, they're the same interpretation of telling us how certain or how noisy are these estimates. Now, we want to use that noise, or the idea of how noisy or certain we are about these estimates, to see if our results are due to chance or due to a systematic difference that's actually reflecting reality. So to check for that, I actually repeated the regression I showed you 1,000 times and collected the coefficient on x, and then I graphed the distribution, or actually a histogram of the distribution of those coefficients, which is the figure you can see here. And the p-value is measuring how far away are our results from 0, or how often are we getting results that are far away from 0. In this case, we had a very small p-value, less than 0.001, and you can see that in my 1,000 replications, I never got a result that was less than about 0.88. Now we want to use the regression to make a prediction, to tell us what do we expect the value of y to be when we change x. And here, our regression equation was that y hat, that's our outcome variable or our dependent variable, equals beta 0, that's going to be our intercept, plus beta 1 hat times x. And beta 1 hat is the slope on x. And we use hats here because these values have all been estimated. We will then plug in a value of x to predict y. So in the example here, suppose x equal 2. Then we would expect y to be 0.005, the intercept, plus 0.972, that's beta 1, times 2, which equals 1.949. And so that's the idea behind using regression for prediction. And as you change the value of x, you get different predictions. So how can we do linear regression practice? Well, we can do that in Excel as long as you activate the analysis tool pack. And I'll be posting a separate video that shows you how to do that. You can also do regression in R, SAS, Stata, Python, and not mentioned on the slide, SPSS is another package where you can do linear regression.